Running to the speech. Okay. For the introduction and the limit type, and this is a joint work with the Thomas Reform, Chen Tan, and the Trevor. Okay, let's go through the background knowledge very quickly. So the differential probability, which was proposed by Meicheng and Shania in 1991. So it studies the probability of a difference propagation. So from that 0 to that 2. So traditionally, it is studied by using the statistical method. So we just cut the summary into many different parts. Here I just give a for example with 2 parts. If we know for the first part, the differential probability is P0, and the second part is P1. So the whole probability can be calculated by multiplying them together. So P is equal to P0 plus P1. For the linear probabilities, the philosophy is somehow similar. So we studied the correlation from gamma 0 to gamma 2. So we also cut the summary into 2 or more parts, and with the knowledge of each part, the linear correlations, we can multiply all the correlations together and for correlation. So by combining the 2 statistical methods, we get the differential linear probabilities. So we studied the linear combination of the output bits. So it's this. Sorry. Okay, with the specific if the difference of that 0. So traditionally, it is also studied by the statistical or the 2-phase method. We just cut the summary into parts. So if we going for the first part, there is a differential with probability P, and for the linear part, the second part, there is a linear correlation epsilon. So we can calculate the full correlation using this formula, P epsilon square. And be careful because some papers are using the bias for this formula, so it's a bit different. Inspired by this, so Meicheng, Stanford, and FSD in 2005 proposed the high-order differential linear analysis. So it's very similar to differential linear analysis. So we also cut the summary into 2 parts. For the first part, if we have a high-order differential with probability P, and for the linear part, we have a linear approximation with correlation epsilon. So the full high-order differential linear correlation can be calculated in the formula P epsilon to D. However, after the proposal of the HDR attack, this is not so popular compared to the differential linear attack. Although the differential linear attack has been very successful in many sufferers, but not too many people know this attack. So it's not right because there are some limitations. So the first limitation is, although the high-order differential, the conception has been proposed to be 30 years, but actually all the high-order differential capabilities are deterministic. There is no probabilistic method to study the probability of a high-order differential. That means for the first part, the P is usually used as 1. That is to say, for the first part, we usually only use the integral distribution rather than a probabilistic high-order differential. And for the second part, you can say the index of epsilon is exponential. So when epsilon is smaller 1, that means the full correlation will go to 0 very quickly. So maybe that means the statistical method is somehow limited. The good news is recently, at the 21st Liu, etc., proposed another direction for the differential linear path. So they use the algebraic method to study the differential linear path. So open a new direction. They found that the differential correlation is actually just the correlation of this. So this is we apply a linear mask to the difference. So if you see the x2 and x2 prime are the number of the input, so it's actually a Fourier function. So that means we can regard the differential linear analysis as to reduce it to a problem to calculate the bias of a Fourier function. So to do this, Liu, etc., just change the method of the propagation of the difference. So they introduce this one called APF, algebraic transitional form. So for the input, you can see the x is the auxiliary Boolean variable. So when x is 0, the input is just x0. So when x is 1, so the input is x0 plus theta 0. That means compared to the statistical method where we only care about the difference, here we actually consider both the value and the difference. So it captures more information. So after the wrong function or some part of the buffer, so we get the x1 plus x delta 1. So if we regard the x1 and the delta 1 as the function of x0, then we go down the x2 and delta 2 can be also regarded as the function of x2, x1 and delta 1 of delta 1, yes. So in a recursive way, we just construct the delta 2 expression, as the x0's function, but in a recursive one. Okay. Yes. So finally, if we have know the expression of x2, then the gamma 2 and delta 2, so we can derive the recursive expression of the differential linear correlation. So we just calculate the correlation. So let's see our contribution. So in this paper, we generalize Liu etc.'s ATF technique to high order keys. So we propose the high order ATF or high order algebraic transitional form. So this is the first method that can predict the probabilistic bias of HDL distribution. Based on this, we found new distinguishers of behavioral types as kind of zodiac. Some are the best for their rounds. The second contribution is another tool called the DSF. So it is a method to linearize Ascom computation. So based on this, we improved some zero-sum distinguishers for Ascom computations. Okay, so let me introduce the first tool called HDF. Let's start with some mathematics. So given a Boolean function f and the input else difference delta, that is a vector. So and the certain input x, so the output order differential can be written in this formula. So you can see that the A is belongs to a affine space. So we just do some variable substitution to make the affine space to a linear space. So you can see M is a linear mapping from a linear space to the affine space. So for convenience, we write the mapping in the x plus x times theta. X and theta are vectors. So by the variable substitution, we just change the reverse formula to the second. So the x is the x belongs to a linear space. So the input of x becomes x plus x times theta. So from a perspective of Q, this is obvious. The output difference, order difference is just the coefficient of x in this Boolean function. Okay, so although in theory now we have the expression of the order differential, however, this is obviously too complicated to write out, let alone to calculate the bias. So inspired by the Liu extension method, we can also use an iterative way to calculate the estimated bias. Yes. So the good news is also almost every software, all the software are built iteratively. So firstly, we write the input of f into a general way. So it's the sum form. So we just when u is 0, then we let alpha u, the coefficient of the piece of the u 0. So it's x. And when u is a unit vector, then we let alpha u, delta I, and for other pieces, they are all there. Here I give you a very simple example for the second order piece. So for the second order high order differential, so the input is this formula. Okay. So next we just apply the one function to input NF. So we get the output NF from the one function. So we can also combine the common monomials, then we get the output. This is very similar, the input. Actually, we can just see the coefficient of every round. So you can see the picture. So from the previous rounds, the 3 coefficient, then go to the 4 coefficient in the second round. And then we can retrieve this state, then we just construct somehow a function. So it's from the input, then go to the next round, until we get the final round. And the high order differential is just the coefficient of the maximum, So this general function, we just call it HATF. So what is the complexity of constructing the HATF? So the most consuming step is to calculate the D different monomial for the mass. Okay, that means we need to multiply D to L monomial AF. So the number of variables is 2 to L, and we need to multiply D of such monomials. So the complexity is proportional to BL. So with the BO position, we can find out the complexity. Okay, the next thing is to based on the iterative expressions that we calculate to estimate the bias of the difference. So a general way is to just use the Asiacrypt formula. So the second level, the one in the middle. However, if we use this level, that means the complexity is very high because the index of 2 there is another 2 to L. So it's very huge. So when L goes up, then the complexity just exploded. Another good news is currently for the suffering for the parameters with quadratic round functions, we can make the complexity much better. So parameters with quadratic round functions are more and more popular for some computations as come to do, etc., or some computing related buffers. And also for these buffers, high order differential related attacks such as the integral attacks or cube attacks are the main threats to them. So for quadratic Boolean function, there is a well-known theory that any quadratic Boolean function can be made disjoint. What is a disjoint Boolean function? So you can see the example. For the first one, there is no variable appearing in any two different quadratic terms. That means it is disjoint. For the second one, x0 appears in both in the first and the second quadratic term. That means it is not disjoint. For quadratic Boolean function, we can just do a very simple variable substitution to make it disjoint. For example, the x0 appears in both quadratic terms, so we just by the monomials, the x1 and the x2 just extracted. So do a simple variable substitution. T0 is just x0, and the T1 is x1 plus x2. So we just made it disjoint. So with this way, it is easier to calculate the bias of F, because firstly we apply the linear explanation M to the input variables, and then to make the first part and the second part, then another system of variables. Then G will be a disjoint one. So firstly, we just use the padding up lemma to calculate the bias of the intermediate variables, and then for the second part of the G, because G is the disjoint, so we can calculate the bias for each part. Finally, with the padding up lemma, then we can estimate the bias of the so with this method, the complexity is not related to the raw variable. It's related to the variable distribution. So this theory, this algorithm is a polynomial. So it's big O to N to 3.8. So because the number of variables in our F is 2 times 2 to L, so the complexity is proportional to 3.8 L. So it's a exponential rather than a super exponential complexity. Okay, but our method relies on some assumptions. This assumption sometimes can cause some problem for the precision. So for the construction of the ATF, it doesn't require any change. So it's mainly for the second step. So the calculation of the bias of variable requires the variable to be independent. But we know, especially for some simple body functions, they are not independent. So we can meet some trouble. So we introduce some solutions to leave the trouble. So the first one is when the variable are linear, then it is more risky not to be independent. So in this case, we just do not introduce a new variable for the next one. We just use the linear approximation, the linear expression, then in the next one. The second trouble is the different bits of RU coefficient can be highly related. For example, if the I speed and the J speed, the two variables are equal or just opposite, that means they are highly related. So in this case, we just do not introduce new variables. We just use one to represent another one. So there are some curves to show how precise our force is, our force are. So this is for the second order HDL approximation for the boron assigning visualization. Say in picture. So you can see at least for the boron assigning visualization, the second order HDL, the blue one is the theoretical estimation, and the red one is the practical the calculation of the bias. So you can see they match very well. For virons, the AF becomes more complicated. So maybe the precise goes down a bit. So not all the highly biased bits can be predicted. However, we can find that whenever our theoretical results predicts that this bit is highly biased, so when we do the practical estimation, practical calculation, we can find that it is true that this bit is very highly biased. And you can also say the peaks and the valleys actually also match with the practical one. For higher order, so for example, the third order to the eighth order, the symptoms are similar. So you can see the eighth order. You can see the peaks and the valleys goes well with practical one. Although there are some gaps, that means it is useful to predict the highly biased bits. So yes, we can do some discussion on precision. I want to stress that the ATF cannot provide any upper or lower bound for HDL biases. At least currently we do not have any theory to guarantee it. However, based on our experiments, we find it's quite precise to predict the biased bits. when the reported bias is higher, the real bias is also higher. So now we have not observed any example of our experiments. So here are some the bias results. So you can see they predict it I think very well. So yeah. Okay. Second story is about the differential order function. So with the high order differential linear expression, so we know that the x and delta actually can be regarded as parameters. So if we choose x and delta in some special value or proper way, then maybe the f can be simplified a lot. So sometimes the algebraic degree can be smaller. But of course, the x and the delta have a very large space, so it's impossible for us to exhaust all the possibilities. So we just introduce an intuition that relates all the x boxes that have the same x plus x delta. So in this way, we only have 32 and 31 choices. Then we exhaust then we traverse all the possibilities. So we introduce the CP4 order analysis. So we find where x bar and that bar are values in a combination in this set, then the algebraic degree of some computation is smallest. So you can see for the 8 ones, the degree is at most 47, but if we use the 48 data, then we can find then we can construct the zero sum distributions. We also apply this method to the inverse function or differential direction. We also find some properties. So for the inside outside zero sum, so the distributions and first we can find the algebraic degree, the 55. Yes, 55. Yes. So we also improve the previous zero sum distribution. However, because our zero sum distributions just fixing the inputs and outputs, that means it's actually different from zero sum, especially the zero sum distribution bound by the different properties. But it also means that our method can capture full information. Okay, let's do a quick conclusion. So we generalize the ATF to the high order case. The HATF is the first method that can handle the probabilistic high order differential linear approximation. Also based on this, we find some new and improved distributions that can recover attacks from the best of the wrongs. And also we propose a systematic method for linearization and finding the sum distribution for Pascal. So all our source code are open resources. Thank you very much. Thank you very much for your attention.
Well, thanks for the presentation. I was wondering how to search for optimal HDL distinguish. Currently, it seems to be that we need to fix the input differential. I mean, from the formula, we need to know the differential delta in advance. We need to fix this question. And I mean the HDL formula. Yes, how do you find the attack for us? Do you need to fix the value delta? The input differential.
The difference.
Yeah.
Okay. Okay. For us, we just use the very low weight, low heavy weight with the difference really 1 bit or 2 bit or 3 bit at most. So we can traverse all the relatives.
So is it possible that there is some high weight different input difference that has a much higher probability?
at least in theory, it is 14 possible. 14 possible. Sorry.
And is there a way to search for this?
Okay, if you use our method, maybe it's not so difficult. Maybe you can just start the search from the beginner part, for example, the second round or the third round with our method with a very low weight difference. Then you can go reverse. So the reverse direction, then you can find other the difference. But I think by intuition, that should be wrong, but the weight of the difference is very low. But it's all about
Any more questions?
And you can see that focusing on the automatic tool concentrating on the type. And I was wondering about that if there are any questions, we can take the include automatic tools.
So basically, I think if some techniques can be used in virtual linear attack, I think it is potential to be used in a higher order virtual linear attack. Automatic search tools. Because the current automatic search tools for the differential linear, actually they are just based on the differential part and the linear part. There is actually no method to handle the process. Actually, I know. So that means you need automatic search tools for the high order differential part. But I know there is a method to handle the high order differential linear, the high order differential. Because
Any questions? Thank you. Thank you again for the talk. The next talk is more example on deep learning and analysis. The authors are Meicheng Liu, Zhang Liu. Then we give the speech.
Hello everyone. This work is explaining deep learning with the cryptanalysis. In crypto 2019, our group proposed the neural distinguisher, and they achieved novel components in the differential neural cryptanalysis. And the neural network is trained to distinguish two types of ciphertext pairs. One type ciphertext pair corresponds to plaintext pairs that have specific input difference, and another type corresponds to randomly selected plaintext. So it can be seen that this neural network is trained with the differential cryptanalysis in mind. But different with the conventional differential cryptanalysis, where the output difference is specified, and the neural network accepts the ciphertext pairs. The Target cipher is the smallest version of the lightweight log cipher stack with 32-bit log, and it is an ARX cipher where and it uses modular addition to provide the non-linearity. So the ciphertext pair will transform into a product of words, and then if the trained neural network will give a score between 0 and 1 to each unlabeled ciphertext pair. And if this score is larger than 0.5, it predicts positive, otherwise negative. And then if we know the real labels, we can evaluate the accuracy of this neural distinguisher. And remarkably, this neural distinguisher achieves a higher accuracy than the distinguisher that uses the full differential distribution table. So this suggests that this neural distinguisher has some additional features that are non-pure different. So what kind of features this can be? So previous work suggests that this neural distinguisher rely on the differential distribution in the last two rows. And this neural distinguisher can make finer distinction than this near difference equivalence class. But what specific knowledge this neural distinguisher learn? So to answer this question, in this work, we try to find the specific patterns that this neural distinguisher could be used to improve the accuracy, and then we use these specific patterns to improve the DDT-based distinguisher. And so in an R1 spec or target, given a pair of outputs, around the last modular addition, we know one output difference, one input difference. And besides, one of the input difference might be predicted because some of the difference might have varies. Apart from these differences, that knows a value. So this known value is the additional information that provide the improvement. But how? So the answer is that when this we compute the differential probability under the known value of this y, that will be greatly different from the differential probability computed under the all possible value of y. The concrete analysis is as follows. The differential propagation through this modular addition that impose at each piece position a linear constant to the value of these inputs and outputs. For example, this xi, this yi, and this ci, where this ci is the s carry. And if we know that at one piece position that a linear constant is satisfied field, then suppose the previous probability we calculated p, and then we know we can adjust the conditional probability b2p. And if we know that this constant is not fulfilled, then the probability becomes 0. Then we use this conditional probability to make the classification that might bring some advantage to classify. So to clarify, then we can evaluate whether the difference constraints can be fulfilled, and we get this table, and we because in spec we know that at the last modular addition only the value of y could be observed. So we try to focus on this last case, C by C case. But this case, it imposes the condition on the XOR of this yi and ci. Well, this carry with ci may seem unknown, but actually depend on the lower bit. So then we know that this lower bit also have some differential constraints on the values and we can get the value of this carry bit. For example, we know that this I and I-1 have this CXY differential constraints. Then we know that xi-1 equals y-1. Then we can know that this carry bit ci equals y-1. And then after analysis, we found that there are many cases where the knowledge of the carry bit can be deduced. Then combined with the previous observation on the linear constraints and this table about the carry bit, we can get many some cases where we can observe the value of y to predict better the differential constraints is fulfilled. These are concrete examples of the differential patterns that I observe the value of y to predict the fulfillment. And interestingly, these constraints on the values imposed by the valid differential propagation align with many previous concepts, including the multi-bit constraints, the quasi-differential, and the extended differential linear approximation. And then we use these observations to increase the DBT-based distinguisher. And the preliminary is to predict the input difference alpha, and this can be done by evaluating some pairs, the bit difference at the right branch of the R-2 round. And then given a pair of ciphertexts, we use the difference to look at the table, the DBT to get the probability. And then we use the output difference data, the input difference, and the value of y to adjust the probability T. And the adjusting rule is largely according to the previous observation and mainly focus on the CYCK. And finally, we use the adjusted probability to make the classification. And then, according to the experiment results, the obtained distinguisher YD could achieve a higher accuracy than the pure DBT-based distinguisher. And so, the previous simple process is fast, but it's required to predict the input difference alpha, and only none of the bits have high values that the predictor can be used. So actually not a full information from the y is used. Then we design a systematic system algorithm to compute the conditional probability. And so in essence, it still uses the output difference, the input difference data, and the value of y, but it does compute all possible input alpha together with the last round probability. And then combine this last round probability with R-y round probability to get the R round conditional probability. And then use the systematically computed probability to make the classification. And in a sense, the concrete procedure involves iterative compute of the next bit of the alpha and using the knowledge of the carry bit and observe some concrete cases with, for example, the CYCK. And it compute the carry bits wherever possible. And then the obtained distinguisher in the ADYD, it finally achieves a higher accuracy not only than the neural distinguisher, this differential table-based distinguisher, but also higher than this neural distinguisher. And so this experiment results suggest that we can use this conditional differential distribution when the input or the output values of the last nonlinear operation are observable. we can obtain distinguisher that surpass the pure differential distribution table with the counterparts. So this neural distinguisher's advantage over the pure difference with the distinguisher comes from exploiting this conditional differential distribution under the partially known value from the ciphertext input to the last nonlinear operation. And these findings apply not only to spec, but also to other block ciphers such as Dylan and Eve. So Dylan, previously we observed that the output goes through the last nonlinear operation. We can fully observe the values. So this could explain why previous research showed that this R neural distinguisher could achieve accuracy close to R minus 1 on the differential distribution-based distinguisher. And for gift, because the key is XOR to only half of the state, and so given a pair of ciphertext, we can get the difference and we can get the half of the values input to the last S-box net. And then we can compute the differential distribution of the inverse S-box conditioned on the partially known value. And then we can, for example, combine R-1, 0.5 from the neural distinguisher and several differential distribution tables based on known values of the S-boxes to get R in the distinguisher. That distinguishers will achieve higher accuracy than this pure neural distinguisher and the DPP distinguisher. And some of them, for example, it can get valid H from the neural distinguisher, but the distinguisher previously don't can get. And besides, we construct various distinguishers for in the related key setting and use many different key difference. And the results show that this ADYD also achieve higher accuracy than this neural distinguisher and this DD. But there is an outlier. You see, this neural distinguisher is achieve higher accuracy than for ADY. So we analyzed it and suddenly found that the correct key state that fulfill the differential trio in the key schedule path will impose that the last round key must have a one bit constantly equals 0. So this last round key does not hide the output of the modular addition in the encryption path. So according to previous analysis, if the probability could be made finite and it can be computed under condition on this known value of the output key. So the neural distinguisher achieve a higher accuracy than the case when the last one's key is randomized. And in another trio, we found that the correct key will have these 10 steps pairs towards 1. And this small pairs was successfully captured and utilized by the neural distinguisher. And this neural distinguisher achieved a slightly higher accuracy than the case when the front key randomized. So from this experiment, we found that this neural distinguisher and the neural network can efficiently exploit the very complex correlations between these ciphertext values, the ciphertext differences, and intermediate state differences. And actually, these observations on conditional differential probability are not intrinsically to the neural network-based cryptanalysis, but they are expected to be useful in wider range of cryptanalysis. And actually, in this work, we have two more subworks. One is to addressing the training tonnage of training higher on the neural distinguisher. And for this, we introduced the 3D layer method. This method can match the rules accuracy, but it cuts the training time and dating. And another part of the work is to introduce the related key difference to slow down the diffusion of the difference in the function paths. So this added in training the neural distinguisher for pair. And as a result, we achieved a 14-round key recovery attack on stack 32 or 64. And actually, there are many future works. For example, how can we explore further this observations and develop the conditional differential cryptanalysis and other traditional cryptanalysis? And in this work, what we did is to explain the machine learning model. And we just provided some reason for the model to achieve the performance. But how to interpret the inner mechanism of the neural network to learn how they express the context relations. And we know that the neural distinguishers are not aware of the specific details of the cycle. And they do not know the S-box, do not know the structure. Therefore, this neural distinguisher can be used for ciphers that have unknown components. However, if the machine learning model becomes knowledgeable about the cipher specification, do they achieve higher accuracy? So how can we let the machine learning model be knowledgeable about the ciphertext specification, so that they can learn beyond this pure data development? So we like this as future work. Thanks for your attention.
If there are no questions, let's take first speaker of this section.